Hello, my name is Sahil Trivedi, and this is my Physics 2211 Lab Report 5 on the human rocket. So getting right into it, we have the introduction, relevant physics principles, our experimental data analysis, or at least looking at the concepts from the video. We have the computational data analysis, results, and our discussion. So the introduction, for the purpose of this experiment, the goal of the experiment is to model free fall and find a way to accurately predict air resistance and drag for the model video that we're going off here. Assumptions are that extraneous variables outside of air resistance and gravity should be ignored. And as for main results, air resistance is just a function of net force, which in turn affects acceleration. The momentum principle is conserved, and you'll see that from the experimental data, or the computational data. So taking a look at the fundamental physics principles, we obviously have principles of position update and velocity update formula, but these really get condensed down into just force is equal to mass times acceleration, as well as the conservation of energy formula. And taking a look at gravity on Earth, you'll see that 0, negative mg, 0 will kind of counteract our drag force moving forward. So taking a look at our initial conditions, the skydiver jumps being affected by both gravity and air resistance. This is from the air particles in the Earth's atmosphere, as well as the gravitational pull from Earth. For our initial position, this is experimentally derived, is 0, 36,576 meters, and 0 in the z. As for the mass, it's estimated to be 100 kilograms. Obviously, the official mass of the skydiver wasn't stated. Looking at the speed of sound, it should be 343 meters per second, and looking at the velocity max, this was determined to be 377 meters per second, and the time was 228 seconds for the final fall. So looking at our model code, on the left side here, you can see that we basically use the same, we're treating the man as a ball or a particle, so the ball mass is considered to be 100 kilograms. The ball position is that initial vector that the man is positioned at, which is that 36,576. The ball velocity is 0, since initially when the man jumps, he's has a 0 velocity and then begins accelerating due to gravity. T is equal to 0 and delta t is equal to our 0.03 iteration, and then gravity is 9.8. Looking at the right side of the screen, you could see that we have this loop running for as long as t is less than 228, since that's the total distance of the fall. And then looking at the ball velocity and ball position formulas, these are just the velocity update and position update formulas put for reference. And then the F net vector will be the acceleration due to gravity and the adding of drag force. And both of these should be displayed on a graph, which we will discuss moving forward. So taking a look at our experimental data results here, even though 0, negative mg 0 is a constant acceleration, or it should lead to a constant acceleration, there is a large amount of air resistance that builds up over time, and you can really see this by the rate that the velocity changes, which is the acceleration, is really diminishing over time. So it starts at that 9.81, but as the man speeds up and feels more of a force of air resistance, he gets slower and slower. And looking at the position versus time, you can also see his position kind of pick up as velocity speeds up, but also it taper off to a certain point. As a man reaches terminal velocity, the graph does start to get more linear, and terminal velocity is simply the point where the drag force is equivalent to the acceleration due to gravity, and that results in 0 net acceleration. Looking at source of air, the drag force cannot specifically be confirmed, since the man's not wearing a monitor to tell us that. There's also extraneous variables that have an effect on the man, like what the suit he's wearing, and then the man isn't actually a particle and experiences different forces on different parts of his body. This is a big reason why, if you were falling in a prone position versus kind of pencil diving, you'll have different rates of acceleration. Looking at discussion 1, if Felix was dropped for a lower height, he may have been able to travel faster than sound. However, he would have needed to be at a certain amount of height for this to happen, and it can't be lower than 6,000 meters if we use the model that we discussed before. And the man will likely reach terminal velocity if he drops from a high enough point, which is where he's no longer accelerating, but this would be higher than the speed of sound. So taking a look at the conclusion, drag force always opposes gravitational force. The air resistance calculated in the experiment is the man pushing against the air particles, and the drag force progressively gets higher, because as velocity picks up, you're technically hitting more air particles at the same time and at a faster rate, so drag force would be much higher. Thank you for watching. That was my Physics 2211 Lab 5. Hope you enjoyed it. Thank you, and bye.